Facebook lost 800 crores in one afternoon. On October 4, 2021, a Facebook engineer pushed a routine configuration change to their backbone routers, but with one wrong command. Within seconds, BGP routes were withdrawn across the entire network. Facebook, Instagram, WhatsApp all down simultaneously for around 6.5 hours. 3.5 billion people couldn't reach friends or family. Businesses that ran entire customer support on WhatsApp went completely dark. The engineer who had physical access to the data center couldn't get in because the door badge system also ran on Facebook's own network. Revenue loss 800 crores in one afternoon. Mark Zuckerberg lost $7 billion in personal net worth that day. That is what happens when a system is not designed for availability. Today, we are going to break down exactly what availability means, how engineers measure it, and most importantly, how you build systems that stay up even when everything else wants to fall apart. Serverpur just built a public library. Let me use that library to explain everything in today's video, because the library makes every concept concrete and memorable. Availability is a percentage of time your system is up and responding to the requests. That's it. Simple definition. But the engineering behind it is not simple at all. In Serverpur, availability asks one question. When a resident walks up to the library door, is it open? Not whether the books are correct, not whether the librarian is friendly. Just, is the door open? Can the resident get in? A system is available if it responds to the requests, even if those responses are slow, even if they are slightly wrong. Availability means the lights are on and the door is open. So how do engineers actually measure availability? Through a concept called the nines. And this is where it gets interesting. Availability is expressed as a percentage. But engineers don't say 99.9%. They say 3 nines. And each additional 9 is dramatically harder and more expensive to achieve. 99% sounds impressive, but that is 3.65 days of downtime every year. For a payment system, that's crores in lost transactions. 99.9%, 3 nines, is the bare minimum for any serious production service. That's still 8.7 hours downtime every year. Imagine your app just not working for 8.7 hours. How many years would you lose? 99.99%, 4 nines, 52 minutes a year. This is where most well-engineered products aim. Most users will never experience the downtime. 99.999%. 5 nines, 5 minutes and 15 seconds per year. This is what AWS and Google Cloud promise for their core infrastructure. Here is the dirty secret. Going from 3 nines to 5 nines doesn't double your infrastructure cost. It can 10 to 50 times your cost. Each additional 9 requires increasingly elaborate redundancy. Now, the two numbers that actually determine your availability, MTBF and MTTR. Learn this and you'll know exactly what to fix. Every engineer talks about availability as a percentage, but behind that percentage are exactly two numbers. Improve either one of them, your availability goes up. MTBF, mean time between failures. How long does the system run before it breaks? Higher MTBF means more available system. How many days does the library run before something goes wrong? MTTR, mean time to recovery. When something breaks, how fast is it fixed? Lower MTTR means higher availability. When the library breaks, how fast does the repair team arrive? Formula of availability is MTBF divided by sum of MTBF and MTTR. This formula reveals something powerful. You can improve availability in two completely different ways. 1. Make failures happen less often. Higher MTBF. Better hardware, better testing, better code. 2. Recover faster when failures happen. Lower MTTR. Automated failover, better monitoring, on-call runbooks. And in practice, lowering MTTR through automation is often faster and cheaper than preventing all failures. You cannot prevent every earthquake in Serverpur, but you can train a rapid response team that rebuilds the library in 10 minutes instead of 10 hours. That's why companies spend millions on monitoring, alerting, and automated failover. They have accepted that failure is inevitable. They have optimized it for recovery speed instead. Before you can build a highly available system, you need to know what you are designing against. Failures come in 4 flavors. Hardware failures. Servers crash, disks corrupt, network switches fail. A single hard disk has a 2 to 5% annual failure rate. At 10,000 servers, failures happen every single day. Inevitable. Plan for them. Software bugs or bad deployments. memory leaks, deadlocks, uncaught exceptions, config errors. A bad deployment is the first cause of outage at scale. The Facebook incident was a software configuration error, not hardware. Human error. An engineer who runs the drop table in production, the operator who deletes wrong S3 bucket, these happen constantly. The 2017 AWS S3 outage that broke half the internet is a typo in a command. Traffic overload or load spikes. Sudden surge of users overwhelming the system. IPL final tweet goes viral and 5 lakh requests per second hit your system instead of 10,000. System was never tested at that scale. So system suddenly becomes unavailable. The mayor of Serverpur asked his engineers, how do we make sure one problem never shuts down the whole city? They gave him one answer. Build everything twice. In engineering, we call that redundancy. And it is the entire foundation of high availability. Redundancy is a strategic duplication of critical system components, servers, databases, network paths, or entire data centers, such that systems remain operational even when individual components fail. Single component whose failure takes down everything is called single point of failure. Finding and eliminating single point of failure is the core work of high availability engineering. Think about Serverpur's main road. One road, one bridge over the river. If the bridge collapses, the entire city is cut off. That bridge is called single point of failure. The fix: build a second bridge. Now one can fail, but life still continues. In systems, you can add redundancy at every layer. Redundant servers, redundant databases, redundant network paths, redundant power supplies, and redundant data centers. There are two types of redundancy: active, passive, or standby. One handles traffic, one waits on standby. When primary fails, standby takes over. It is cheaper, but there is a brief downtime during switch. For example, main library is open. Backup library is staffed, stocked, but door is locked. If main library burns down, backup library opens in 2 minutes. Active. Both systems handle traffic simultaneously. If one fails, other absorbs all traffic instantly. Zero downtime, but higher cost. Both are fully provisioned. For example, 2 libraries are opened simultaneously, serving different areas. If one burns down, everyone goes to other, so zero closure time. February 28, 2017, an AWS engineer was debugging a building system issue. While following a runbook, they mistyped a command and accidentally removed a much larger set of servers than intended from the US Eastern S3 cluster. S3 went down, and because S3 is used by thousands of apps as the storage backbone, a huge chunk of internet went offline with it. Netflix, Slack, GitHub, Trello, all broken simultaneously. Root cause: no redundancy across regions. All S3 capacity for those apps was in one region. One wrong command took it all down. AWS added region level redundancy protections shortly after. Now let's look at the actual high availability patterns engineers use to implement redundancy in production systems, load balancers, and multiple servers. The most basic high availability pattern: traffic is distributed across multiple servers. If one crashes, others keep serving. Health checks automatically detect and remove failed servers from the rotation. Database replication and read replicas. Primary database handles writes. Read replicas handles queries or read queries. If primary fails, a read replica or secondary replica is promoted. 80% of DB operations are reads. Replicas offload the primary dramatically. Multi-region deployment. Deploy the same system in multiple geographic regions. If Mumbai data center goes down, Singapore takes over. Users are routed to nearest healthy region automatically. Health checks and automatic failover. Every 5 to 30 seconds, the system checks each component. Failed component detected, traffic automatically rerouted in milliseconds. No human needed. This is what makes MTTR near zero. Graceful degradation. When a component fails, the system continues in reduced capacity rather than crashing entirely. Netflix stops showing recommendations when the ML service is down, but streaming still works. Partial availability is still better than zero availability. Let me leave you with 5 things from this video that will stick with you forever. Availability. Percentage of time the system is up and responding. Simple question: is the door open? The nines. 99.9% is 8.7 hours down per year. 99.99%, 52 minutes. 99.999%, 5 minutes. Each 9 costs exponentially more. The formula of availability is MTBF divided by sum of MTBF and MTTR. Lower the MTTR through automation. It's faster than preventing all failures. Redundancy. Redundancy eliminates single point of failure. Active-active, zero downtime. Active-passive, brief switch time. The goal is not zero failures. The goal is that failures never reach your users. Serverpur's mayor learned this the hard way. You cannot prevent every disaster, but you can build a city where one disaster, flood, fire, power cut, does not shut down the entire city. Before you build anything new, ask what happens when this breaks and how quickly does the backup take over. In the next video, we are looking at reliability, which is availability's close cousin. See you there. Thank you.